So, ladies and gentlemen, it's 6 p.m. Central European Time. I'm your host for today's session, talking about fast and easy electronics thermal management in collaboration with our customer Forwiz System. Let us briefly talk about the agenda for today. So I'll first introduce Seongsu Park from Forwiz System, as well as my colleague Alexander Fischer from SimScale. We'll then move on to the CPU cooling case study performed with SimScale, and this will be presented by Seongsu Park. We'll then move on to Alexander Fischer, who will talk about harnessing the power of the cloud using SimScale. And before the Q&A and discussion series or part, we will briefly talk about the hands-on workshop case taking place next week. So as already mentioned, we are joined by Seongsu Park from Forwiz System. And talking about Forwiz System is an IT service focusing in the field of system integration, network and software development based in South Korea. There are about 70 employees and 5 people working dedicatedly in the thermal division section. I'm your host for today's session, and my name is Youssef Murad. I'm the product marketing engineer here at SimScale. And I'm also joined by my great colleague, Alexander Fischer, who is product manager at SimScale and also co-founder of SimScale with plenty of experience in thermal management and electronic solutions. So who is SimScale? SimScale was founded in 2012 in Munich, and we're a SaaS company focusing on engineering simulations. We have a headquarters in Munich, but also offices in New York as well as Boston. And we basically created the world's first cloud-based engineering simulation platform where you can perform computational fluid dynamics simulations inside of your browser, as well as solid mechanics simulation, but also thermodynamics applications. And everything is accessible via a standard web browser. So as already mentioned in the introduction or talking about the agenda, we will talk about the optimization of a CPU cooling case using SimScale. We will discuss the key setup parameters and demonstrate how to set up this case and how we could derive specific results for this case. So with that being said, I'm now handing over to Seongsu, who will talk about the CPU cooling case study. Over to you, Seongsu.
Okay, thank you, Youssef. So hi everybody, it is my pleasure to meet you all. I'm Seongsu Park from Forwiz System. I'm very happy to have this opportunity to share with you our experience working with SimScale to tackle important problems for our projects. So I'd like to begin with the target system of interest in today's talk, the CPU cooler. So in many cases, the important parts of CPU cooler consist of heat pipes and heat sinks. A heat pipe is a rapid heat transferring device with very high thermal conductivity, up to tens or hundreds times higher than that of typical metals. And it basically utilizes the latent heat absorbed and released during the phase change of working fluid inside heat pipe, mostly water for CPU cooling cases. Heat pipes rapidly transfers heat generated from the CPU to heat sinks, and then the role of the heat sink is to increase the contact area with airs to accelerate the final dissipation of heat into the surroundings. And for effective performance of CPU cooler, we need to optimization for each component. So there was a request from one of our clients that they want to improve the cooling of their CPU inside their 2U servers. The problem they had was that the CPU chip they were using has many CPU cores, and the CPU coolers that are readily available in the market is not providing enough cooling capacity. And as a result, when the CPU chips are fully operational, the CPU temperature easily exceeds 90 Celsius degree, and that's why they cannot make their CPU chips fully operational. Also, the positions and arrangement of different components inside their servers was pretty much fixed, so we could apply some slight changes for the improvement of this cooling. So in order to solve the address problem in the simplest manner, we basically came up with 3 ideas. So first, we tried to fully utilize the surrounding space for the CPU cooling so that we increase the width of the upper part of the heatsink. And secondly, we tried to add more heat pipes to deal with the increased sized heatsink. And so thirdly, in addition to this, we can apply a special paint that has high thermal radiation emissivity, so that we can utilize the extra thermal radiation from the heat sinks. Yeah. So in order to test these basic ideas, we first build the prototype coolers with and without applying radiation paint, and we perform a series of experiments to see the difference from the difference between the newly proposed cooler and the benchmark cooler. So from the experiment, we get this result, and from this experimental result, it can be easily seen that the structural change significantly increased the performance when compared to the benchmark cooler. But at the same time, it seems that the effect of the radiation paint can additionally decrease the temperature further. But like how much the effect is will be vague in terms when compared to the effect of the increase of the surface area. This point was important for us because the application of radiation paint will require extra cost and manufacturing process. So we want to know if the application of radiation paint really worth it. Yeah. So at this point, we contacted our client so that we can further test the prototype coolers we made with actual server. And what we found out is that the newly proposed cooling concept indeed can make the CPU fully operational and reduce the CPU temperature around 80 Celsius degree. It fluctuated around 80 Celsius degree, but still we made this improvement. So at this stage, we were around only 5 degrees off from the target temperature. So the client wants their CPU working at 75 Celsius degree. So at this stage, we try to see we can optimize further. So at this stage, we try to use the SimScale simulation to do this optimization. So we put our simplified model in a 2U chassis model and model the fans with velocity inlet, pressure outlet boundary conditions. We also utilize the radiation feature of conjugate heat transfer analysis version 2 of SimScale simulation. And heat pipe is modeled as a combination of the heat pipe shell, which is copper, and its inner region, whose thermal conductivity is about 10,000 watt per meter Kelvin, which is about 25 times bigger than the thermal conductivity of copper. And we applied 150 watts to the model of CPU, and we set the ambient temperature to 25 Celsius degree. So from the simulation, we could first check the effect of the radiation paint in details. The CPU temperature in the heatsink. So when we look at the temperature in the heatsink region, it seems like the temperatures is more evenly distributed. And as observed in the actual experiment, we could observe the 3 to 4 degree temperature reduction when we use the emissive paint. At this stage, you can safely say that this amount of difference is really due to the application of the radiative paint, not some minor difference that was caused by, potentially caused by the manual assembly process. And about the geometry of the heatsink, we investigated a couple of more points. The first point was that we initially thought that our placement of heat pipes somehow could block the air flowing path. And what if we adjust the connecting position of heat pipes to upper heatsink a bit lower? However, when we adjust the position of heat pipe a little bit lower, and when we see the result from the simulation, we get the result opposed to our initial thought, because it seems like it adversely affects the entire cooling performance of heatsink, because the temperature of CPU is increased by about 2 Celsius degree. So in order to understand this result, we checked relevant literatures, and we also can draw similar conclusion from the literature study. For example, the graph excerpt from this reference suggests that the combined thermal resistance of two heatsinks of 25 millimeter height, which is half of 1.175, about 0.085. This number is smaller than the combined thermal resistance of, for example, the heatsinks of 37.5 millimeter height and 12.5 millimeter height, which is about 0.92, or like one single heatsink of 50 millimeter height, which is about 0.11. So this simulation result is suggesting that the effect of increased thermal resistance of the heatsink when we place the heat pipe a little bit lower, so this effect is bigger than the advantage of reduction in air path blockage by heat pipe. So this simulation result is really giving us the insight that it's better to just position of heat pipe to the center of this heatsink. So likely, we also had to optimize other geometric dimensions. For example, the fin spacing. If there are too many fins placed too densely, they can choke the airflow. But at the same time, when the fin is in too sparse distribution, meaning that means too small surface area can be used for the cooling. So we really have to find the optimal spacing for the given conditions. Also for the fan power, the literature suggests that the optimal fin spacing decreases with the increased fan power. So when we think the air velocity of fan and the fin spacing and fin length and fin height, we think those parameters as input, and we try to find the optimal fin geometry based on the simulation. So we really need to find the optimal geometry with several parameters such as air velocity, fin spacing, and fin length and fin heights as input. And when we do the simulation to find the optimal condition, rather than performing the simulation for the entire assembled geometry, we rather perform the simulation with only the heatsink geometry. And from the simulation, we could observe similar trend, which can be found in the literature. So with this process, we optimize the geometry of heatsink with the given conditions. And as we already had this kind of data when we made the prototype version, the fin spacing was quite close to the optimal condition. And in the new version, we tried to increase the number of fins by using fins of smaller thickness, which is harder for the manufacturing. But if it increases the performance, then it is gonna be worth it. And from the simulation, we could see that indeed, by using the more number of fins, you can further decrease the CPU temperature. And even in this result, the difference seems a little bit smaller, but that's because these results are not in a complete equilibrium. So what we plot here is that the the graph, which have the which we get from the series of described simulations, the CPU temperature versus the simulation time. So in order to get the final equilibrium temperature, we try to fit the data with the exponential curves, and we put the final result in the table below, and we can see that the according effect of radiation paint and the structural change. So from the simulation, we concluded that the radiation paint actually worked, and from the structural optimization, we can decrease the CPU temperature by 3 to 4 degrees. And based on this result, we improved our entire CPU cooler design, and we manufactured it, and we performed the actual experiment, and we could really observe about 3 to 4 3 to 4 Celsius degree decrease in CPU temperature, and the client was happy about it. So in summary, our concept of using extra surrounding spaces for cooling amounts for the decrease in about 15 Celsius degree in CPU temperature, and the use of highly emissive paint further accounts for the decrease in the temperature for 4 Celsius degree, and the optimization of heatsink geometry further decreases the temperature by 5 Celsius degree. So with these ideas combined, we were able to give a satisfactory answer to the client request. So that's it from my side, and thank you for listening.
Great. So thank you, Seongsu, for this example, how you use simulation at Forwiz with SimScale. I will now give you all a bit of a understanding of what SimScale can essentially do in general for electronics cooling problems. And I will also want to give some specific insights into how the cloud can specifically in thermal management applications help you to make flexible and very powerful use of simulations. And I want to start this off essentially by giving you some understanding of how SimScale works. And I want to do so by just showing a bit the differences about the traditional approach to entering simulation, how it was done in the past, and now how SimScale and how cloud simulation in general make a difference to this this traditional approach. So if you want to buy essentially or use simulation, there were a lot of things in the past that we identified as barriers to using simulation that we wanted to get rid of. That's kind of the whole idea of SimScale. So all is centered around accessibility, and some of these barriers are obviously related to costs, and these are usually hardware and software costs. So if you want a simulation, you need to purchase now first a software package that can do this for you, and obviously you need now the hardware to do so as well. So you cannot just run this on a tablet. You need some computing power, you need some memory to do so, and that means you have already some quite high upfront costs to start using simulation. Now with SimScale, this changes heavily because we are a platform, we are a software as a service company. So everything you need to start simulating on SimScale is essentially a laptop, a stable internet connection, and a browser, because that's how you access the simulation. All of the hardware and software part is done by getting a SimScale account and starting to do so. So that is already makes it much more accessible to everybody to start simulation, and all of the handling of the complex part of hardware and software is done by us. There's a second barrier that we identified, and that is that there's many engineers that are not making use of simulation, even though it would be to great effect for them, simply because there's some know-how barrier, that there is not the knowledge about how simulation can be used, and that's why there's some fear essentially to even get started, and that is how we started even developing the SimScale user interface. So it's meant to be very easy also for beginners, but specifically we also have a very different approach to support. So you don't, if you run into an issue with your simulation setup, or you might have some questions around how to model specific real case physical entities like radiative paint, as we heard of, then you don't need to actually file now a support ticket in some support system and then wait for an email answer and open up a long thread. You directly essentially reach out to one of our experts in the live chat in the user interface, and can obviously also call them and talk to them about the problems that you have. And we will also later see that we want to offer you some nice intro into using simulations as part of these webinar / workshop series. Additionally, what is obviously troublesome with traditional simulations is that if you actually bought the hardware that you require, it's always a trade-off between costs and efficiency, right? So you might want to run a couple of simulations at a certain time, and then later on maybe not. So it's always a trade-off, and it always means that you as a person are not as efficient as you should be, as you're just running simulation after simulation in a serial manner, and that costs you quite some time. And obviously, in some cases, you could make more use of more cores or a more powerful hardware in the back end, and that's also what changes heavily with SimScale. And I want to show you how we increase your productivity around that, mainly in the next slides. So first, maybe a quick introduction. What does Cloud CFD even mean, right? So if you look at the process when you're doing a simulation, this involves multiple steps. So that starts essentially with uploading your model, inspecting it maybe a bit. You want to potentially do some CAD modifications, and maybe remove some components that are not relevant for your simulation, create the flow regions, etc. Before you go on, set up your simulation with all of the parameters that are needed, run the simulation, then during the run, check on the progress, maybe even at a weekend or from home, analyze the results once the simulation is done, and at the end, share this with your client or your colleagues. That's essentially the step through the simulation process. And during this process, all of these steps that you see here have different requirements for you in regards to software and hardware, right? So visualizing the model and analyzing the results essentially need a good GPU. You want to really render this model fast and have valuable insights. On the other hand, putting together the simulation setup does not really have high requirements in regards to CPU and GPU power at all, while on the contrary, once you're running your simulation or run even multiple simulations, you really now need the power, you really now need the hardware. And what Cloud CFD means in these regards is that, for example, SimScale picks now for each and every step of this workflow the exactly right hardware that you require, that you are most efficient, and that you can make most out of these stages. So this is not up to you. We pick the perfect, essentially, setup for you to do what you right now want to do. And specifically in regards to these running multiple simulations, thermal management and electronics cooling simulations are a great example of why you can make extensive use of this. And this is specifically because in thermal management, what we are trying to is we want to optimize for certain goals, right? And usually this is some junction temperature of chips or some critical components that you want to reduce or keep in a certain target area. And to do so, you have different strategies of achieving this. We saw this very well from the example that Seongsu presented, and also the different parameters that Forwiz System was looking at when trying to reduce the temperature of the CPU chip. And this often comes down here. You see some examples to the heatsink design itself, to material choices, thermal interface material choices. This comes down to really, do you do passive cooling, active cooling with fans where you can pick different components, or maybe liquid cooling via heat pipes, via liquid cooling channels. So there's many options that you have around it. For all of these, you can pick now some parameters, and you want to see essentially how they influence your result and what's the most effective and what's also worth it in regards to unit economics, right? So is it worth the price? Is it worth to put the radiative paint? And what's the increase in performance that you gain from investing a bit more into the cooling strategy? And what simulation allows you is now doing all of this in some way of virtual testing without needing prototyping, etc. So why this is so beneficial, we can also look at by first looking how was it done, or how is it done if you're not using simulation. What does physical testing based design workflows require? And that is first, you actually need to build that prototype. Often this involves then maybe a second company or a partner. Often it's done abroad. So you need to first manufacture the prototype, then it needs to be shipped, and then you run it in your testing environment. So essentially, this already requires quite some time. It's also costly, so a couple of hundreds to maybe lower thousands of dollars that such a test requires. So that means it limits you or the number of design iterations, optimizations that you can do to a smaller number. So maybe a few, maybe just one or two. And it also forces you in a way to be on the safe side with what you're trying to do in regards to design. So you maybe put a bit more material than is needed and over-engineer essentially your solution to, in the end, not lose time and be still fast in regards to putting your product to the market, right? Simulation can help here a lot, right? Because what you can see, the turnaround time comes down from days to weeks, really down to hours, right, for each simulation. That means you can maybe run 10 plus simulations and do this within a 1 or 2 weeks, or in the turnaround time of usually physical testing. The costs are dependent on what you purchase in regards to hardware and software, but you can already do a lot more. You can already test a lot more. And that is definitely beneficial to your setup. And now we can look at what cloud simulation actually does to this. And it's in a sense very simple. It brings down the turnaround times for all of these simulations that you do or you would want to do to the turnaround time of one simulation. So essentially hours for all iterations, and the costs now, at least in regards to SimScale, are also pointed out here. And that simply is because we have unlimited computing power. We can run all of these simulation runs in parallel. And we can also make use of the most efficient hardware setups for each run, right? So if you're running a small simulation, we might pick a smaller hardware instance in the background. But if it's really a compute intense, we can go up to 96 cores. And each of these simulations then also comes down to a lower turnaround time. So specifically for iterative design processes where you want to do a lot of optimization steps, this is just incredibly beneficial. And how this is done then in the end in the simulation setup, we also saw already from the example beforehand. But in essence, what we want to do, we want to see really the critical components temperatures. So we want to see the conduction in the solids and the temperature field in the solids. But we also want to really see how the flow fields in liquid cooling channels or natural or forced convection of the air around the whole assembly. We want to see how does this affect the solution. And in many cases, we really don't want to estimate, for example, convection coefficients. We really want to see what the actual physics do. How does our convection system work here, and take all mechanisms of heat transfer, conduction, convection, and additionally radiation into account. And that's what we usually do in a so-called conjugate heat transfer analysis. And that's where also SimScale heavily invested over the last year to make this as efficient as possible, make it possible for you to run all of these different iterations in parallel, but also be very efficient for each job by running it on powerful hardware in the backend. So that's how essentially such a setup is done. And obviously you have access to all of the electronic specific components and features that you require. So you can use obviously fans with a fan curve. You can use liquid cooling channels. You can switch radiation on and off dependent on if it plays a role. If you have high emissivity in the model, you can model your chips obviously with compact thermal models. But to show you how that actually works, we think the best case is essentially to put you hands-on such a case, experience it yourself, right? Test it out yourself. Also test out how then these iterative studies can be done in SimScale. And that's why this webinar series is essentially a two-part series. We have now the webinar today, but we will also have a workshop where we want you to get your hands dirty essentially on our software, test it out, and have already the benefits of the close support that we also apply to our customers by our application engineers helping you with doing exactly this.
Thank you so much for attending. It was a very active series as I could see from the attendance rate. And we will now move on to the Q&A section. And I've seen during the webinar that you also sent us some questions, especially for Seongsu. Maybe Seongsu, you want to answer the first question, which is how many different setups did you run for this case? And how often did you vary the heatsink design? I mean, we saw it in the plot, right? Also about the radiative paint, how did you change that? Was it like binary? Did you use no paint and then paint? Maybe you can go a little bit into depth here.
So, like, of course, the number of the iteration depends on the application. I don't remember the exact number, but the range of it would be like 50 to 100 iterations. But as I already explained in the presentation, I didn't, when I do this kind of optimization, I don't do the simulation for the entire structure, but rather I perform the simulation for the heatsink only with very good layers. And when I find the, for example, the local minimum of the target temperature, during the target parameter, then I stop there. So, and the simulation cost for the simulation of only heatsink doesn't amount much. So, even if with all this iteration, that doesn't surmount to like a very big amount of computational cost.
Mm-hmm. Great. Regarding the radiative emissivity, was this provided by the supplier? How did you get to this number?
Actually, we get this number from the supplier. We didn't do any like extra experiment in order to check this. But as the experimental result somehow matches with the simulation result, I think the number is trusted.
Great. Along those lines, what are the main advantages of using heat pipes for CPU cooling compared to, for example, fan cooling or immersion cooling?
So actually, heat pipes are not like new device. Heat pipes have been used in used for the cooling of many different devices so far, including the CPU cooling. But what we did here is to produce a tailor-made cooler that can maximally make use of the given arrangement of computational parts from the client side. So, and even if the heat pipe-based cooling is nothing new, but I think in the future, everything must be combined to give much better output. So, for example, and when we see the example in, for example, the automotive cars, sometimes the entire chassis can be used as a heatsink, and sometimes the liquid cooling is combined with the heatsink plus heat pipe. So in this case, liquid cooling is actually used for the cooling of the heatsink. So I think they are not competing with each other, but rather we have to combine those things in order to get the best result.
Excellent. Thank you so much, Seongsu. And we have a last question coming in, which is how do you set the thermal conductivity of the heat pipe? And how sensitive are the simulation results to this?
Yeah, so actually the effective thermal conductivity of the heat pipe is changing with many different parameters. This is different from the like just fixed materials such as metal or plastic. This is really a lot of things can affect this parameter. So, for example, the working temperature and the length and diameter of heat pipes. For this reason, we often vary this parameter in a reasonable range to a certain degree to how much this change in this parameter results in the final target temperature. And from my experience, the dependency of this final result on the effective thermal conductivity of heat pipe starts to saturate when this value exceeds the threshold value. And with this, we can get this reasonable potential range of the final target temperature. So this is the process of doing the simulation and get the some trustable range of final target temperature.
Mm-hmm. Excellent. So that have been all questions so far. Is there anything else you would like to add, Alex, from your side?
No, really interesting questions also in regards to the application. If there's any other questions around SimScale and how this really works, right, I can just recommend you to sign up for the workshop and ask all of your questions simply there with Matt and Steve. And thanks, obviously, for listening in.
Thank you so much. Also, big thank you to Seongsu for participating in the webinar and also presenting this case to us. And thank you also so much for a lot of people participating in this webinar. With that being said, have a nice day, evening from wherever you're watching right now, and I'll see you in the hands-on workshop. Bye-bye.
Thank you.
Bye.
Bye-bye.